Welcome you all. We will be talking today, continuing with the thermodynamics. और आज का जो टॉपिक होगा वो स्पेसिफिक हीट होगा. या स्पेसिफिक हीट कैपेसिटी भी कहते हैं. तो स्पेसिफिक हीट हम जो स्टडी करते हैं तो एक ऐसा फिजिकल क्वांटिटी है जो कैरेक्टराइज करता है चेंज इन टेम्परेचर को जब हम सिस्टम से हीट लेते हैं या जब हम सिस्टम को हीट देते हैं. अक्सर हम देखते हैं कि अगर हम सिस्टम को किसी भी सिस्टम को हीट देते हैं तो उसका टेम्परेचर रेज हो जाता है फ्रॉम T1 टू T2. या अगर हम इसको कूल्ड करते हैं, इफ वी कूल द बॉडी, तो इसका टेम्परेचर भी कम हो जाता है. तो स्पेसिफिक हीट एक फिजिकल क्वांटिटी है जिससे हम ये जो कूलिंग या हम जो हीटिंग सबस्टेंस को करते हैं उससे कितना टेम्परेचर रेज हो जाता है, तो उसके लिए हम स्पेसिफिक हीट स्टडी करते हैं. सिंपली जो स्पेसिफिक हीट के रिलेशन है दैट इज Q इज इक्वल टू mc डेल्टा T. राइट लाइक दिस. दैट इज हीट जो चाहे वो सिस्टम को दिया गया है या सिस्टम से लिया गया है, चाहे हमने सिस्टम को हीट अप किया है या सिस्टम को हमने कूल्ड किया है, दैट हीट is directly proportional to mass of the material, that is mass of material, and that heat directly proportional to the temperature difference, that is delta T, that is T2, or you can write T2 minus T1. यानी कि टेम्परेचर इंटरवल कितना है, तो टेम्परेचर कहाँ से शुरू हुआ, कहाँ तक रेज हो गया, या कितना टेम्परेचर पहले था, कितना डाउन हो गया, वो जो इंटरवल है उसके ऊपर भी हीट डिपेंड है, स्पेसिफिक हीट डिपेंड है. जो इसकी रिलेशन है दैट इज ये प्रोपोर्शनलिटी खत्म करने के लिए वी गेट Q इज इक्वल टू Cm डेल्टा T, और C इज स्पेसिफिक हीट कैपेसिटी and delta T is a temperature difference, and this Q is the heat required to change the temperature of the body. अब ये चेंज वर्ड क्यों लिखा है कि यहाँ रेज भी हो सकता है, यहाँ कम भी हो सकता है बॉडी का टेम्परेचर. हम हीट ले लेंगे सिस्टम से या अगर हीट सिस्टम को दे देंगे तो उसका टेम्परेचर रेज भी हो सकता है. दैट्स व्हाई वी पुट डाउन द वर्ड चेंज इंस्टेड ऑफ रेज. सो दिस इज सिंपल इक्वेशन फॉर अ मटेरियल ऑफ मास m. सो वी कैन राइट इट its unit specific heat constant. You can write it like this. C is equal to Q bata m delta T. Suppose if the object has mass, the material has a mass 1 gram, and we raise the temperature by 1 degree, then the interval is equal to 1 degree. 1 degree or 1 Kelvin in a SI system. The interval here is that it means that you can take the, in case of water, you just like take from 14.5 to 15.5. How much heat you required to raise the temperature from 14.5 to 15.5. Here I just write the interval only. The difference must be 1 degree. In order to raise the temperature of a body by 1 degree, say suppose if you have an object at A, it is at 30 degree. How much heat you need to supply to raise the temperature by 30, to raise from 30 to 31, and if the mass of object is 1 gram. So you can write C is equal to Q divided by 1 into 1. Then C is equal to Q. Hence, specific heat capacity is a heat required to raise the temperature of 1 gram of substance by or through 1 degree. So specific heat capacity is the simply heat required to raise the temperature through 1 degree. So it is SI unit. You can write the SI of specific heat is you can write it's here joule. In the SI unit, it is a joule, Kelvin, and kg. So you can write this joule, K inverse, kg inverse, or its SI unit is joule, kg inverse, C inverse. Sometimes you take in terms of calories also. Heat is taken in terms of calories. That is another unit. But we are preferring here mostly SI system. That's it. Is the unit of this uh, specific heat. Or in terms of calories, you can take calories per gram uh, per Celsius raised minus 1. This is also the unit of specific heat in terms of calories, and this in terms of joules. You're right. So this is the equation for the specific heat for any material. So I can write it also in this way. Suppose a small change in temperature. So small change, that is due to infinitesimal change in temperature, infinitesimal change, temperature change due to this heat dq. Suppose the dt is the infinite small change in temperature for the quantity heat q dq. Then you can write it dq is equal to mc delta t. Or you can write specific heat is equal to dq over dt into 1 by m. M is the mass of the material. This is also how to write the specific heat, that is dq over dt, that is change in heat with respect to temperature. This is the equation with respect to mass of the material. Now, since in thermodynamics we are dealing with the gases, but in case of gases the situation is different. In case of gases, there are many thermodynamical processes for which we have different state variables like pressure, volume, and temperature. And at different, here we are studying the variation of temperature, but during the variation of temperature in thermodynamics, sometimes for isochoric process we keep volume constant, and sometimes for isobaric process we keep pressure constant. What about the specific heat capacity in gases? So the specific heat in gases has a quite different situation as compared to when we study the specific heat for solids or liquids. Now, let us discuss the specific heat capacity for the gases and molar specific heat when we take the gases in terms of molar gram, or when we take the gas into the moles. How we can put down the specific heat and how we write the specific heat capacity in case of gases. So we know before that, putting down the specific heat equation for the gases, let me tell you, we have 2-3 isobaric, we have a thermodynamic process like isobaric, keeping volume constant, keeping pressure constant, we have isochoric, keeping volume constant. Now the specific heat, molar specific heat, so m is replaced by mole, so we can write C Q is equal to mu C delta T. So instead of mass, we now replace the number of moles. This is a molar specific heat capacity. So I can write C is equal to, for a small temperature change, the quantity of heat required, that is dq, is equal to mu C delta T. So you can write dq over dt is equal to mu C, or C is equal to 1 by mu dq by dt. In terms of when I write the mass, then I put down like dc is equal to 1 over m dq by dt. This was in terms of mass. Now this is in terms of number of moles. And here we are talking about the gas. See, if we have discussed it so far, all the thermodynamic processes taking into consideration the ideal gases. So let us discuss the molar specific heat for the ideal gas, or the simply for gas molecules. So we are discussing here the mu, so the molar specific heat, that replacing this m by mu. So now, as I discussed earlier, that during the thermodynamic processes, we have isobaric and isochoric processes, where in both the cases the temperature variation is there, and in specific heat we are raising the temperature by giving the heat to the system, or we are taking away the heat from the system by lowering the temperature. So in both the cases the temperature variation is there, but we have thermodynamical processes varying. That's if it is isobaric, the pressure is constant. If it is isochoric, volume is constant. What happens to the specific heat in terms of gases when we talk about the gases? So now let us discuss the specific heat at constant volume and the specific heat at constant pressure. So in case of gases, there are different definitions for the specific heat in the terms of constant volume and specific heat in terms of constant pressure. That was not supposed to be happening in other materials like solids, but in here in gases we are taking the thermodynamic process into consideration. Then according to that and accordingly we will discuss the specific heat for different thermodynamical processes. So I have equation C is equal to 1 over mu dq by dt. This is the equation for this for some moles of gases. Let me discuss now. If I talk about the gases, then we have to put down the energy of the gas molecules. If we consider the total energy is kinetic, and we know the kinetic energy is actually the internal energy, and that internal energy is equal to that we have discussed early in our early previous lectures, 3 by 2 nRT, where n is the number of moles. And if I write the same internal energy in terms of number of molecules, then I can write 3 by 2 nkBT. This is Boltzmann's constant, here it is gas constant. And if I write the same equation in terms of P and V, then I can write 3 by 2. This nRT is equal to about PV is equal to nRT, and I know instead of nRT I can write PV. These are the three equations, same three equations representing the internal energy of the system when that energy is completely taken as a kinetic. So the kinetic energy or the internal energy, and internal energy is a function of temperature. So the internal energy is 3 by 2 nRT, and same can be written in terms of Boltzmann's constant 3 by 2 nkBT, or the same energy can be written as 3 by 2 PV, because you know nRT is equal to PV. This in terms of pressure and volume, how we write internal energy. This is in terms of Boltzmann's constant and temperature, how we can write. This in terms of gas constant temperature, how we can write. So I have to make the use of those very equations. Then I discuss the specific heat at constant volume and the specific heat at constant pressure. Since I know the equation that I have for the specific heat is equal to 1 over mu or n, small n, dq by dt. This is the number of moles. Now if I take n is equal to 1 and the temperature interval 1 degree, that's called molar specific heat, to raise the temperature of 1 mole of substance, 1 molar of substance by through the 1 degree. So I have to put down n is equal to 1 and dt temperature is equal to 1 degree. Then Q becomes equal to CV. There's a molar specific heat. Similarly, as you did write specific heat, when you take the mass m is equal to 1, here I take n is equal to 1. There's 1 mole. So now discussing the whole equation, let me discuss now for n equal to 1. For a 1 mole of substance, for 1 mole of gas, now let me discuss the specific heat capacity at two thermodynamical variables, keeping first volume constant, then keeping a pressure constant, and just discussing where the specific heat is maximum, where we will need more specific heat capacity. So at equation C is equal to n dq by dt, where n is the number of moles, I am not discussing that n is equal to 1 for a 1 mole of gas, that you know that mole specific heat. So I get C is equal to dq over dt. I put n equal to 1. Now we will be discussing first specific heat at constant volume. Specific heat at constant volume, represented as CV, is equal to dq by dt at V. This is representation of specific heat at constant volume. Now this is the equation that I have. As we know the thermodynamics first law, now using the thermodynamics first law, you have dq is equal to du plus pdv or dw, that you know, pdv. That if you give the system a heat, amount of heat is required to raise the internal energy, is converted into internal energy, and the rest of the energy is required to do the work. Suppose we have in this gas is a working substance, we are supplying heat to the system. यहाँ पे हम सिस्टम को हीट दे रहे हैं. ऑब्वियसली हमें पता है अकॉर्डिंग टू फर्स्ट लॉ, आधी एनर्जी जो है वो इसका इंटरनल एनर्जी इंक्रीज करेगी, यानी इसका टेम्परेचर इंक्रीज करेगी, और आधी एनर्जी जो है वो इसको एक्सपैंड करेगी फ्रॉम V1 टू V2. द वॉल्यूम इज नाउ चेंजिंग फ्रॉम V1 टू V2. In both the cases, isobaric and isochloric, the temperature is changing. Suppose I am taking this container where piston is at this place, and after supplying the heat, it moves from V1 to V2. There is change in volume, there is expansion. Suppose I keep volume constant. I am not changing the volume, volume is constant. Then process is isochoric. This volume is constant. What happens when volume is constant? V is equal to constant. Your dV comes out to be equal to 0. The expansion is 0. That means, according to first law, this dV is equal to 0. You are supplying the heat. There is a completely change in internal energy. There is completely change in internal energy. Because this V is constant, this dV becomes equal to 0. Your heat is completely converted into internal energy. So the temperature increases rapidly. So the specific heat, you can say in other words, जो टेम्परेचर है वो बहुत जल्दी बढ़ जाएगा. ऑब्वियसली क्योंकि आपका सिस्टम एक्सपैंड नहीं हो रहा है, कोई वर्क डन नहीं हो रहा है, वर्क डन इज 0. Here dV is equal to 0 means V is constant, वॉल्यूम इज कांस्टेंट. ये पूरा पोर्शन 0 बन जाएगा, यानी कि वर्क डन 0 हो जाएगा. तो आपका सारी हीट जो है वो इंटरनल एनर्जी में कन्वर्ट हो जाएगी. जब इंटरनल एनर्जी में कन्वर्ट हो जाएगी, टेम्परेचर जल्दी से रेज हो जाएगा. तो यहां टेम्परेचर रेज करने के लिए आपको इतनी हीट नहीं देनी पड़ेगी. तो इसका मतलब है यहां की स्पेसिफिक हीट में उतनी एनर्जी की ज्यादा जरूरत नहीं है. आपको थोड़ी हीट देने से इसका टेम्परेचर बाय 1 डिग्री रेज हो जाएगा. तो इसका स्पेसिफिक हीट उतना ज्यादा नहीं होगा comparatively when we talk for the isobaric process. If I may now take into consideration isobaric process, I am talking first. I talked about the isochloric. Now I am talking about the isobaric process. This is V1. This is the phenomena where V is constant. You are not changing. You are giving the supply of heat. Internal energy increases. Temperature increases from T1 to T2. But in this case, your volume is increasing from V1 to V2. Here, pressure is constant. Here, volume constant. अगर आप इक्वल अमाउंट ऑफ हीट दे रहे हैं यहां से भी और यहां से भी, लेकिन यहां पे वॉल्यूम चेंज नहीं हो रहा है. Here, no expansion takes place. The heat is completely converted into internal energy, means it raises the temperature very rapidly. While in this case, when you supply the same amount of heat, its volume is expanding. There expansion takes place. यानी कि गैस ने थोड़ा काम कर दिया, उसने वर्क भी कर दी. यहां वर्क 0 हुआ, लेकिन यहां वर्क अब इस मामले में कांस्टेंट प्रेशर के मामले में वर्क डन 0 नहीं हो रहा है. इसने कुछ काम भी कर दिया, इसने एक्सपैंड भी कर दिया, इसने पिस्टन को अप कर दिया. तो इसका मतलब है यहां वर्क भी हुआ, उसने थोड़ी एनर्जी ले ली, और थोड़ी बहुत एनर्जी इंटरनल एनर्जी ने ले ली. स्मॉल अमाउंट ऑफ एनर्जी इज टेकन बाय द इंटरनल एनर्जी. तो यहां उतना तेजी से टेम्परेचर रेज नहीं होगा एट कांस्टेंट प्रेशर जितना एट कांस्टेंट वॉल्यूम पे होगा. सिंपल सी बात है. एट कांस्टेंट वॉल्यूम देयर इज नो एक्सपेंशन. All energy, heat supplied is converted into internal energy that enhances this temperature because internal energy is directly proportional to temperature. In case of isobaric process, there is expansion, there is work done by the gas, that amount of heat is converted into work and rest of amount energy is converted into internal energy, that didn't cause that much change in the raising the temperature. So here will be less raising temperature as compared to this one. So यहाँ पे specific heat कैपेसिटी हमें टेम्परेचर रेज करने के लिए हीट ज्यादा देनी पड़ेगी, ताकि इसका जो टेम्परेचर डिफरेंस है उसके लिए हमें ज्यादा हीट देनी पड़ेगी. तो इसका मतलब है स्पेसिफिक हीट एट कांस्टेंट प्रेशर इज ग्रेटर देन द स्पेसिफिक हीट एट कांस्टेंट वॉल्यूम. यहां टेम्परेचर जल्दी रेज हो जाएगा, इसका मटेरियल का टेम्परेचर जल्दी बाय 1 डिग्री रेज हो सकता है. यहां जल्दी टेम्परेचर रेज होने वाला नहीं है, क्योंकि यहां आधी जो हीट सप्लाई है वो वर्क में कन्वर्ट हो गई. इस वजह से यहां पे आपको और टेम्परेचर बढ़ाने देना पड़ेगा, ताकि इसका स्पेसिफिक हीट बढ़ेगा तो टेम्परेचर बढ़ाएगा. तो द स्पेसिफिक हीट इन केस ऑफ कांस्टेंट प्रेशर is greater than the specific heat as constant volume. So you can now write that specific heat at constant pressure is greater than specific heat at constant volume, क्योंकि यहाँ वर्क डन भी होता है, जिसकी वजह से इंटरनल एनर्जी उतनी नहीं मिलती है और उससे टेम्परेचर उतना रेज जल्दी से नहीं होता है. यहाँ वर्क डन 0 है और उस वजह से इंटरनल एनर्जी को पूरी एनर्जी मिल रही है जो जल्दी टेम्परेचर रेज करता है. तो इसका मतलब यहाँ स्पेसिफिक हीट कम है, यहाँ स्पेसिफिक हीट ज्यादा है. Now how we can discuss it mathematically? So I put down here equation that's dq is equal to du plus pdv for constant volume. Your dv comes out to be equal to 0. For constant volume, your dv comes out to be equal to 0. So there is change with respect to temperature dividing by dt on both the sides, du by dt plus pdv over dt. Obviously, the constant volume, pdv is equal to 0, so you can write dq by dt is equal, this is constant volume, means isobaric, isospheric at constant volume. But the specific heat at constant volume, like this, I can write as Cv, as I told you earlier. So this is d by dt of u. Instead of u, I told you this for 1 mole, so n is equal to 1. When you have a 1 mole, your u is equal to 3 by 2 RT. This equation, you can substitute instead of u, that is 3 by 2 RT, and this becomes 0 because dV is equal to 0. So this is specific heat at constant volume is equal to differentiation of this 3 by 2 RT to R d by dt of t, that's 1, t की जगह 1 होगी, you get C by C, C is equal to 3 by 2. So the specific heat at constant volume for 1 mole of gas, 3 by 2 R. Similarly, I will take the same equation now. I will take the same equation. Now, specific heat at constant volume. The symbol is like this. So I can write dq over, we know that according to first law, dq is equal to du plus pdv. At this very moment, the constant is pressure, the volume is changing. So dv cannot be equal to 0. So by differentiating with temperature, dq over dt is equal to du by dt plus d by dt of pdv, because we are checking the variation with the temperature, so I just divided throughout dt. So I can write dq by dt. At this moment, the pressure is constant, so I can write it Cp. So this is d by dt of u. I can, for a 1 mole, 3 by 2 RT, and plus d by dt of, I can write d of PV. Sometimes you write d by dt of m into v. Sometimes you write m into d by dt of v. कांस्टेंट अंडर मल्टीप्लाई करने से कोई फर्क नहीं पड़ने वाला है. मैंने एक कांस्टेंट अंदर ले लिया, और दो कांस्टेंट है लेकिन मैंने अंदर ले लिया, कोई फर्क नहीं पड़ेगा. इस तरह से कभी हम लिखते हैं चेंज इन मोमेंटम, कभी हम m निकालते हैं चेंज इन वेलोसिटी. दोनों सेम ही इक्वेशंस है, वही मैंने यहाँ पे लिखा है. So I can write Cp is equal to dq by dt at constant pressure is equal to, the differentiation is 1, you get 3 by 2 r plus d by dt of, so I have written it double times d2, it's pv, I should take it p d by dt of p d is like this, p dvt, then I can write it d by dt of pv. So I can put pv is equal to, pv comes out to be equal to RT, because for one mole PV is equal to RT, and I substitute here instead of d by dt I write RT. So Cp comes out to be equal to dq over dt at P is equal to 3 by 2 R plus R, because differentiation of P is 1. So 3 by 2 R plus R is equal to 5 by 2 R. Hence, specific heat at constant pressure comes out to be equal to 5 by 2 R, and specific heat at constant volume becomes 3 by 2 R. This indicates that specific heat is greater than, at constant pressure is greater than specific heat at constant volume. This is a simple equation that you mathematically prove that the specific heat at constant volume is 5 by 2 times R, while specific heat at constant volume, constant pressure is 5 by 2 R, while the specific heat at constant volume is 3 by 2 R. This indicates that Cp is greater than Cv. Now, what's the difference between this Cp minus Cv? So you have Cp minus Cv is equal to 5 by 2R minus 3 by 2R. This comes out to be equal to C pi of Cv is equal to 2 by 2R, that is R. इसको आप सिंपली R कॉमन निकाल सकते हैं, 5 by t minus 3 by 2 is R into 5 minus 3 is R into 2 by 2, get R. So the difference between the constant specific heat at constant pressure to specific at constant volume is equal to the gas constant R. Now the question is, and early I talked about the N is equal to 1. This is a 1 mole of gas. I didn't discuss which type of gas it is. And from this very point, I can take which type of gas this is. Since I consider the total energy as a kinetic, that means I'm absolutely talking about the monoatomic gas. So before this, a discussion was journal. It was general discussion for a 1 mole of gas. It can be any gas, it can be diatomic gas, it can be triatomic gas. But here, as we have taken completely the energy as a wholly and solely kinetic, so it was a monoatomic gas. We were talking about the monoatomic gas. For a monoatomic gas, your specific heat at constant volume at constant pressure is 5 by 2R, and specific heat at constant volume is 3 by 2R for a monoatomic gas. If there is now a diatomic gas, what about diatomic gas? For monoatomic gas, gases or molecules are completely randomly moving, there's a completely kinetic energy. But when it is a diatomic gas, the situation is different. There could be vibrational energy, there could be translational energy, as well as rotational kinetic energy. That will be discussed in the next chapter for a different part of diatomic and triatomic gases. We will discuss specific heat. Thank you very much.